Every year, humans generate over 2 billion tons of waste worldwide, and glass accounts for nearly 20% of that total. Here's a fascinating scientific fact. A single glass bottle can remain intact in a landfill for over 1 million years without decomposing. Unlike organic materials, glass doesn't break down through biological processes. But here's the remarkable part. Glass is one of the few materials on Earth that can be recycled endlessly without any loss in quality or purity. The molecular structure of glass remains stable through infinite recycling cycles. So how does this transformation actually happen? How do piles of broken, dirty shards become crystal clear bottles ready for use? Today, we're taking you inside one of the world's largest glass recycling facilities, where hundreds of tons of glass are transformed every single day. You'll discover the engineering, chemistry, and technology behind the incredible journey of Earth's most sustainable material. Let's explore this 5 billion recycling business together. For glass recycling to work efficiently, facilities need a consistent supply of used bottles and containers. In everyday life, empty bottles are often mixed with regular household trash, which makes the sorting process both expensive and time-consuming for recycling centers. However, many countries have developed innovative solutions called reverse vending machines or bottle deposit systems. Here's how they work. Consumers place empty bottles into these automated machines, which use optical scanning technology to identify and sort each container. In return, users receive a small refund, typically between 10 to 25 cents per bottle. This system achieves two important goals simultaneously. It incentivizes citizens to participate in recycling. It provides recycling facilities with pre-sorted, cleaner glass that's easier to process. Studies show that bottle deposit systems can achieve recycling rates of up to 90%, compared to just 30–40% in areas without such programs. When collection bins reach capacity, specialized trucks transport the bottles to recycling facilities. A single full-size truck can carry between 20,000 and 30,000 bottles, approximately 10 to 12 metric tons of material per trip. At the facility, trucks unload their cargo into massive storage bays. Within minutes, colorful mountains of glass, greens, ambers, and clears accumulate in the yard. These aren't just piles of discarded material. They represent the raw resources that will fuel the entire recycling process. The recycling process begins when industrial loaders scoop up large quantities of waste glass and deposit them into the plant's feed hopper. Steel conveyors immediately begin transporting the mixture, glass combined with dirt, sand, and various contaminants, into the facility. The first processing station uses vibrating screens that shake at high frequencies. This mechanical action separates dust, grit, and tiny particles from the larger glass pieces through a process called size separation. Even with advanced machinery, human oversight remains essential. Workers stationed along the conveyor carefully remove paper, plastics, and other materials that automated systems might miss. These trained technicians develop an experienced eye for contaminants, often spotting materials that sensors overlook, items like rubber gaskets, plastic film, or unusual ceramics. This combination of mechanical screening and human inspection ensures a cleaner batch of material, typically improving purity by an additional 2 to 3% beyond what automation alone achieves. Many bottle caps are made from steel or aluminum, which must be removed before glass can be melted. The solution is a high-powered magnetic separator. Using powerful electromagnets, this system creates a strong magnetic field that attracts and removes ferrous metals while allowing non-magnetic glass to continue along the conveyor. Some facilities employ multiple magnetic stages with increasingly powerful magnets catching progressively smaller metallic fragments. For non-ferrous metals like aluminum, facilities often use eddy current separators. These systems employ rotating magnetic fields that induce electrical currents in aluminum, effectively repelling it from the glass stream. After this stage, the glass is approximately 80% free of contaminants. Now comes a crucial transformation, converting glass pieces into cullet, the industry term for crushed recycled glass. The hammer mill. Large glass pieces enter a hammer mill, a machine containing high-speed rotating hammers that pulverize the glass through repeated impacts. These hammers can strike glass fragments at speeds exceeding 1,000 RPM. Any pieces that remain too large are automatically detected and recirculated through the mill until they reach the correct size, typically between 5 to 50 millimeters depending on the intended application. Scientific benefit. Cullet melts at lower temperatures than raw materials, Using cullet can reduce energy consumption by up to 40% compared to manufacturing glass from virgin materials like silica sand and limestone. This happens because the molecular bonds in glass have already been formed. Reheating simply returns the material to its molten state without requiring the complete chemical transformation needed for raw materials. The cullet then passes through a powerful pneumatic system. Strong air streams strip away any remaining label fragments and lightweight debris, further purifying the glass particles. Multiple air jets positioned at strategic angles create turbulent airflow patterns that lift paper and plastic, while heavier glass fragments continue their forward momentum along the conveyor. This is the most technologically advanced stage of the entire process. As cullet cascades through the sorting system, laser sensors continuously scan each fragment, analyzing color, wavelength, chemical composition, size, and shape. When the system identifies a piece that doesn't belong, whether it's the wrong color glass or a ceramic contaminant, it fires a precisely timed burst of compressed air, diverting that piece into a separate stream. The reaction time is measured in milliseconds, with pneumatic valves responding faster than the blink of an eye. Fascinating fact: modern optical sorters can process tens of thousands of individual glass pieces per minute with remarkable accuracy. Color separation is critical because even small amounts of incorrectly colored glass can affect the final product's appearance and quality. Once sorted, cullet travels along conveyor belts to designated storage areas separated by color: clear, green, and amber. These stockpiles await their transformation into brand new glass products. Manufacturing the recipe for glass cullet alone cannot produce new glass. It must be combined with specific raw materials in precise proportions. SiO2, the fundamental component that gives glass its transparency and structure. Silicon dioxide forms the glass network, creating the amorphous, non-crystalline structure that makes glass transparent. High-purity silica sand containing 95% or more silicon dioxide is essential for producing clear, colorless glass. Soda ash, Na2CO3, also called sodium carbonate. This flux lowers the melting temperature from approximately 1,700 Celsius, making the process more energy efficient. During heating, sodium carbonate breaks molecular bonds in the silicon network, allowing it to flow at lower temperatures. Limestone, calcium carbonate adds durability and chemical stability to the finished glass. Without limestone, glass would be water-soluble and chemically unstable. Calcium ions integrate into the glass network, creating stronger molecular bonds that resist weathering and chemical attack. Manufacturers may include dolomite, alumina, or metal oxides to adjust specific properties like color, strength, or heat resistance. Iron oxide creates green glass, while cobalt oxide produces blue. Manganese dioxide historically served as a decolorizing agent, neutralizing the green tint from iron impurities in sand. The role of cullet recycled glass typically comprises 20% to 70% of the total batch. Here's why this matters. Every 10% increase in cullet content reduces energy consumption by approximately 3%. Using cullet significantly decreases carbon dioxide emissions. Cullet melts more uniformly, improving overall product quality. The blended mixture enters massive gas-fired furnaces where temperatures reach approximately 1,250 Celsius to 1,500 Celsius, even hotter than volcanic lava. Safety note: workers in these environments wear specialized protective equipment, including heat-resistant suits and heavy gloves, as ambient temperatures can approach extreme levels. The mixture is carefully monitored as it transforms. Over approximately 24 hours, the solid ingredients gradually liquefy into molten glass, a dense, glowing mass with the consistency of thick honey. For the next several hours, the molten glass remains at temperature, allowing trapped gases to escape. This fining process ensures the highest purity and clarity in the final product. Tiny bubbles of carbon dioxide from limestone decomposition and other gases naturally migrate to the surface and dissipate, leaving crystal clear molten glass. Before any bottle can be made, engineers must design and manufacture precision molds. Using computer-aided design, CAD software, engineers create digital models specifying exact dimensions, wall thickness, and surface details. These designs must account for how glass behaves during cooling and solidification. Glass contracts approximately 1 to 2% as it cools, and mold dimensions must compensate for this shrinkage. Molds are manufactured from cast iron or specialized alloy steel, capable of withstanding repeated exposure to temperatures exceeding 1,400 Celsius. A single mold might produce millions of bottles before requiring replacement. Most glass bottles are created using a technique called blow-and-blow molding, one of the most reliable methods for producing hollow glass containers. Molten glass is precisely cut into portions called gobs. Each gob has a specific weight and temperature, approximately 1,000 Celsius, for optimal forming. The gob drops into a preliminary mold. A burst of compressed air from above pushes the glass outward, creating a hollow parison, essentially a bubble-shaped preform with a finished neck. The parison transfers to the final mold, where a second air blast expands the glass outward until it conforms precisely to the mold's contours. Every valve and sensor in modern bottle-forming machines operates with timing accuracy measured in thousandths of a second. This precision enables facilities to produce hundreds of thousands of identical bottles daily. Fresh from the molds, bottles glow with residual heat. Robotic arms carefully transfer each bottle to conveyor belts leading to the annealing layer, a controlled cooling tunnel. Why controlled cooling matters? If glass cools too quickly, internal stresses develop that can cause cracking or shattering. The annealing process, lasting anywhere from several minutes to over an hour depending on glass thickness, gradually reduces temperature, allowing molecular stresses to dissipate evenly. Modern glass facilities employ sophisticated quality control systems, optical sensors, and high-speed cameras. Every bottle passes through inspection stations where cameras capture multiple images per second. Advanced software analyzes each bottle for cracks or fractures, air bubbles within the glass, surface scratches, dimensional variations, warping or deformation. Any bottle failing inspection is automatically removed from the production line. Special attention goes to the bottle opening. Automated systems rotate each bottle while optical sensors and mechanical probes check for chipped edges, microscopic cracks, dimensional accuracy, critical for proper cap sealing. Only bottles passing all quality checks proceed to packaging. Robotic palletizing systems organize thousands of bottles efficiently. Suction cup mechanisms grip entire rows of bottles. Bottles are arranged in precise layers on pallets. Protective sheets separate each layer. Automated wrappers secure pallets in protective film. Tracking codes link each pallet to its production batch. Finally, pallets move to warehouse storage, ready for distribution to customers worldwide. Glass bottles ultimately serve a purpose, containing products we use daily. Beverage bottling demonstrates the final stage of a bottle's journey, where industrial precision meets consumer expectations. Before filling, every bottle undergoes thorough cleaning to meet strict hygiene standards. High-pressure hot water rinses remove any dust or particles from manufacturing and transport, followed by steam sterilization at temperatures exceeding 170 degrees Fahrenheit that eliminates bacteria and microorganisms. Caustic solutions may be applied for stubborn contaminants, while air jets blast away remaining moisture. Final inspections with UV light and sensors confirm absolute cleanliness. Modern bottling facilities process these cleaning steps in seconds per bottle, maintaining both speed and safety. High-speed filling lines showcase remarkable engineering, processing thousands of bottles per hour with mechanical accuracy. Automated nozzles dispense exact volumes, measured to the milliliter, while counter-pressure filling prevents oxidation in sensitive beverages like beer and wine. For carbonated beverages, carbon dioxide is injected under carefully controlled pressure to maintain consistent fizz. Temperature monitoring ensures products are filled at optimal conditions, and real-time sensors verify fill levels on every single bottle, rejecting any that fall outside specifications. The fastest production lines can fill over 2,000 bottles per minute, a testament to decades of industrial refinement. Immediately after filling, bottles enter the sealing phase, where crown caps, twist-offs, or cork closures are applied with precision machines generating exact pressure. Torque sensors verify every seal meets specifications, while induction sealing creates tamper-evident bands on certain bottle types. High-speed cameras inspect for cracks, chips, proper fill levels, and correct labeling. Metal detectors ensure no foreign objects contaminated the product, and any defective bottles are automatically ejected and recycled back into the glass stream. This multi-layer quality control ensures that only perfect products reach consumers. Before packaging, bottles receive their final identification, High-speed applicators attach labels with precision alignment, while laser or inkjet printers add production dates, batch codes, and expiration information. Barcodes enable tracking throughout the supply chain, and some facilities use embossed codes directly in the glass for premium brands. Bottles then continue along conveyors to automated packaging stations, where robotic arms or mechanical guides group them into precise arrangements. Cartons are formed, filled, and sealed in continuous motion with shrink wrap or cardboard dividers protecting bottles during transport. These cartons are assembled onto wooden or plastic pallets using specific patterns that maximize stability. Stretch wrap secures the loads for shipping, and finished pallets move to climate-controlled warehouses where temperature and humidity are monitored. Distribution networks coordinate delivery to retailers worldwide, often within 24 to 48 hours of production, and so the glass's journey comes full circle. What began as broken, discarded shards, perhaps a wine bottle tossed in a recycling bin, a jam jar from someone's kitchen, has been transformed through heat, precision, and human ingenuity into something pristine, valuable, and ready to serve again. That same glass might hold tomorrow's craft beer, next week's pasta sauce, or next month's artisan honey. This cycle can repeat infinitely. The bottle you recycle today could return to your shelf a dozen times over the coming decades, each iteration requiring less energy and fewer raw materials than creating new glass from scratch. Glass is infinitely recyclable. Unlike plastics that degrade or paper that weakens, glass can be recycled endlessly without any loss in quality or purity. Using Cullet reduces energy consumption by up to 40% compared to melting raw materials, translating to millions of tons of carbon dioxide prevented from entering our atmosphere annually. From optical sorting that identifies colors in milliseconds to precision-forming machines that shape molten glass, modern engineering has made mass recycling not just possible, but economically viable. Each recycled bottle conserves raw materials like sand, soda ash, and limestone while reducing environmental impact. Globally, recycling 1 ton of glass saves over a ton of raw materials. The glass recycling industry employs thousands of workers and generates billions in economic activity, proving environmental responsibility and economic success can align. Recycling glass isn't just beneficial for our planet. It's a remarkable demonstration of how science, engineering, and community effort can transform waste into wealth. We hope this exploration has given you a deeper appreciation for the journey every glass bottle takes, from the recycling bin through intense heat and precision machinery back to the shelf, and perhaps inspired you to make recycling part of your daily routine. Every bottle you recycle contributes to this elegant, endless cycle. Thank you for learning with us today. If you found this educational, please consider sharing it with others who might enjoy discovering the science behind everyday materials. Until next time,